Hello, we are back for reviewing the temporary structure design book. This is the cover of book by Chris Souder. I have reviewed the first 9 chapter in Farsi, but it's been over 1 month from my last recording, and uh, to be honest, I almost forgot most of the things for this chapter, for the chapter 9. Uh, I wanted to review again, but then I decided, since I decided to continue my YouTube channel in English, I said, okay, it's a good exercise as long as I don't have that much viewer, so I think it can be very helpful for me. I have my tablet here and also my OneNote, everything that, let me try one more time. I think it's not updated yet, just give me a couple of seconds. Okay, I'm just trying. I wrote a couple of formula from previous chapters. I just want to see if I write something here, it will show in my laptop. Okay. It has a short delay, but still it's working. If I draw a cube here, after a couple of seconds, it will show on the screen. So it is okay. I'm okay with that. Uh, so I know from this chapter we're going to formwork design. I'm not gonna review what I have reviewed in the from the book, and for the English word is not it. This is not just teaching. I'm not going to teach. I'm not at the I don't see myself at the level of teaching. This is just reviewing the book, and the reason that I'm doing this is that I think everyone should know where to find related information, and by reviewing the books, you can have it in your mind in the that you can refer to the book and follow everything. So we are going to review the formwork design. I think I have reviewed this part in Farsi, in the Persian, or Farsi, I guess. But I started to explain this, but this time a little bit faster in English. This section is going to talk about the formwork design. There are 3 parameters that is going to affect our formwork design. Okay, the first one is a formwork design. It's just like other designs. Members, we have loads, then we have codes, standards, or anything formula, then we check. But for the loads comes from concrete pressure. For the concrete pressure, this equation that you can see here is a simplified one. There are other equations you can follow from ACI, which I explained in previous videos, but right now it's not part of our scope. We are assuming that we calculated the pressure on the formworks. Normally the diagram of the pressure in the formworks given the ACI is something look like this. This is P max, and there is always CW and CC as 2 modification factors. This one for the unit weight, and this cc is for chemical material in the concrete. The R is the rate of the concrete, and T is the temperature. These are, I think, the most important things that you know, how you should know about how to design the concrete pressure. But for the continuum, for this part, we are assuming that, okay, we have the pressure, and we have three different let me find a better word. We have uh, three different condition, not criteria to check. First, bending, shear, and deflection. And the bending, for the bending part, we have again different material members. Sheeting, the OBS sheeting, a stud, Waler. For the shear, again, we have we check the shear for sheeting, stud, and Waler, and the deflection, all the same. Before we continue, it's important to know the load pass in the concrete formwork, which is something that is going to be our major factor for the design. For each page, I try to keep the screen. If you want to read the whole screen, you can pause and read it. I also put the book in my Telegram channel, which you can find and under the video, so you can download the book as well. For the bending stress, there are two different approach for considering the design. For the bending stress, as long as we are considering those members, the studs or the beams or the sheeting, as pin beams, so we can use the equation M equal to W L to the power of 2 over 8, and based on the maximum allowable stress, we can calculate the section and the spacing. But the main thing that this chapter is doing, because the sections that we are using in the formwork design is normally 2x4, 4x4, members are wooden members like Douglas fir or stuff. We are knowing our S, so the only parameter that we normally check and design is the spacing of the members. For example, we have a formwork, we have the pressure from the previous equations. Then we go, okay, say if we use 2x4, if we use 4x4, what is the maximum allowable distance between these members, for example, between studs? Or if we want to use sheeting, what is the maximum space that we can put our studs to the sheeting is in the range of the allowable stress. If we increase the stud spacing from that range, the sheeting is going to fail. The approach is like this. Let's go for the next. Okay, here in this one more important thing that in this slide that we can talk about is the load pass. How the pressure is going to act. It comes from the concrete to the plywood, then to the stud, Walers, and ties. It's very important to know these steps, because how we design from plywood. Based on the equations, we calculate the maximum spacing for the studs. Then we go for the studs, and based on the equation we calculate the maximum span that a stud can be without any support. That span, that equation will give us the spacing for the Walers. If I show in the my OneNote, the steps is let me imagine this is our formwork. I'm looking in a front view, okay? So these these pink members are our stud, and the green one is the Waler. You're looking in the front view, okay? And the pressure comes from, if looking that way, the pressure is like, that's the concrete, the pressure to the wet concrete. Okay, the first step is 1. I will mention stud 2, and this one 3. The load pass, as I explained, comes from the concrete to the plywood to the stud, and then Waler and ties. Okay, so the first thing that we design, first we have 3 different equations, which I'm gonna put it in the OneNote. Let me just before this equation comes from here. The first equation is 10.9. We could then solve L for the span by using the following formula. I'm not going to read everything here, but the maximum here, the most important one is this one. Let me take a snap from here, copy. Let's come from here, put it here, paste. We could solve L span by using the following formula. This formula is the same for plywood and dimensional lumber. So basically this formula is for plywood and dimensional lumber. We can use this equation. So for this equation we have FB. There is one in the following picture page. There is one page that explains all the formula with what is every of these FBS or W is. I'm not gonna waste time here because I'm not gonna teaching you. This is something that I'm doing most to teach myself. Okay, for the shear stress right now, from the bending for plywood and dimensional lumber, we can use this equation. For the shear, again, there is some explanation here, and if we comes down, we reach 2 different. I'm sorry, someone calling. Just a sec. Sorry, it was a very long phone call. I forgot what I was saying, but here it's talking about the shear stress, and for the plywood the equation would be similar to this one, and for the dimensional lumber the equation would be something like this. Let me add this one also on the OneNote. Paste shear. This is for bending. The next, and for the deflection, the maximum deflection, again you can read the whole paragraph, but I'm just going to use this equation, and let me put it on the OneNote. Okay, this equation comes for deflection. So basically, so far we have three different criteria: bending, shear, deflection. And each of these has its own equation for give us the maximum length that a member can be under the pressure from the concrete wet concrete, and then we can continue. Okay. The load pass is typically, I mentioned earlier, comes from the concrete formwork to the sheeting, and from sheeting to the stud, and from a stud to the Waler, and from Waler to the ties. It's important also, let me put it here. This is the load pass. Okay, let me make everything a little bit more. Okay. Here's talking about the uniform loads on form members. The most important aspect when following the load path is determining the uniform load on the next beam member to which the load is transferred. For example, this paragraph is very important. That's why I'm going to read the whole paragraph. The most important aspect when following the load path. Okay, we were here. If, for instance, if it is determined that the studs are to be spaced 14-inch on center to support a plywood thickness, then the uniform load on the stud must be taken into account the 14-inch spacing. So basically, what is saying the uniform load that a member can is 14-inch multiplied by the maximum pressure that we obtained from the equation from the concrete pressure. This uniform load on the stud becomes P max, which is the maximum pressure, multiplied by, if P max is based on the foot, so we multiply by 14 inches divided by 12 inches to gives us the P load per linear foot. For example, if the P max was 800, our load be 933. This is very important. And there are some adjustment factors for material stresses. For example, for shear, the ACI allowed us to increase the twice, or for the load duration, shear adjustment, wet factor. These are something that we can use for different materials. For example, for the wood, we have different, these are all based on American modification factor. In Canada, in the CSA 86, I think 086, we have different modification factor. The basic concept behind it is very similar to what we can see on the screen, but that's it. I think it's a good to let me review. Okay. I think it's good to review the example, but before doing the example, this is a table with common wood species allowable stresses, because most of the formwork based on the wood member. This is something that I think it's good that we have it here. And what I'm gonna do, I have a plan to solve the example, every detail, even the calculation. Because what I understand that if you do that, it's gonna sit or sink in your mind better. The FV is the shear stress, the FB is the bending stress, and E is the module of elasticity. For example, if we dive more on this table, for the Douglas fir larch, the bending stress is 1000 psi. The compression perpendicular to grain is 6 to 25. The compression parallel to grain is 1600. You see the difference, it's almost 2.5 times stronger. The horizontal shear is 95 psi and module of elasticity. This table for different type of material, different type of wood species: Douglas fir larch, Douglas fir south, southern pine, pine, SPF, hemfir, and OES plywood. This table comes from National Design Specification, which is for American codes. For the plywood, the most important thing that we should know, putting plywood, it has two different that the grain or orientation of the grain is very important for the plywoods. If it's parallel to the span, the orientation is parallel to the span, it's in the strong axis of the plywood. If it's perpendicular to the span, it's in the weak axis. Here we have most common equation for calculation in plywood. This is for bending parameter, shear, and deflection. Okay, for the shear we have IB over Q, which we can use from the table for each different member with the plywood with different thickness. Like you can see, for example, for 1/2 inch member, we have two different okay, for 1/2 inch, I don't like this color. Okay, this is better. The minimum ply is 3 ply, and we have a strong moment of inertia, a strong section modulus, and IB over Q for a strong section and weak section. It depends on the orientation of the plywood. The strong section is when the plywood exterior face grain runs parallel. Here it will tell when strong and when is the weak. It depends of the orientation of the grain in regard to the span. Here is a stud and Waler design. In this section, talking about the stud and Waler size, have many more options, so the rules of material of selection have more range. For instance, this stud selection using range of 2x4, 2x6, or 4x4. And for the Waler, normally we double the studs. Let's say we have a stud 2x2, 2x4, or 4x4. For the Waler, we double these 4x4 and use it as a Waler. What else that is important is section modulus of this member, which is our section is rectangular. So I'm not sure, I'm sure this is easy, but the section modulus, let's say we have let me show it here. Let's say we have a rectangular section. This is B, this is D. S is equal to I over D over 2. Okay, in this case, it would be B, D over 3, 12 over D2, which is B, D2 over 6. This is something which for a strong axis, and for the weak is the reverse, is dB2/6. This is for a strong section of modulus, or S, this is weak. Okay, weak S. And these are the steps of the formwork design which we are going to follow. Let me take a snapshot of this step also, put it here, paste. We are gonna do every single of these steps in the following example. Okay, let's dive a little bit on this picture, or let me take a snapshot. The reason that I'm taking so much a snapshot, because I can use draw with my pen in my tablet, so it's very important. Okay, as you can see in this picture, we have these members are our studs, okay, on the blue line, and on the red these are the Walers. Oh, this is a platform that works. I think this is the Waler. Still, I'm not sure. I cannot find the Waler. The Waler normally is the horizontal member. Okay, what happened? Let's say these are the Waler. I'm gonna show the Waler. I cannot find it here. Let's say these are the Walers, and the red one is our plywood. Okay, let's go back to the steps. The first step is calculate the pressure from equation, which comes from the previous chapter. After that, we go determine the plywood type and thickness. Okay, because this is a design problem, we are going to use 2x4. We are going to use 4x4. Then we obtain every information about that one, and start from load pass equation. The first load pass comes to our sheeting. Based on the sheeting, we have three different criteria. We have bending, we have moment, we have shear, we have deflection. We will check all of these equations. The minimum amount of spacing from each of these equations obtained, it would be our stud layout. So then we have our stud layout. We multiply with this spacing by the pressure and act our stud as a beam, as a pin beam, so we calculate the maximum amount of length that this stud counts as a simple span beam. That length also comes from three different criteria. Comes from shear, comes from deflection, comes from bending. After that, when we calculated that length, then that length would be our Waler spacing as well. Then we calculate, check every single of these for our Walers. We calculate based on the shear, bending, and deflection, which we will follow in the example. Okay, let's go to the example. I don't want to make the video more than 1 hour, so let's go to the example. In this picture, this is important to have a look. If we consider we can consider our problem in two different ways. Let me talk about this one as well. If we want to look our problem as each of these sheeting as a simple pin example, and put our sheeting something like that, or we can put our sheeting a continuous member, something like this, with a long continuous member, which is we can use the uh, as a continuous equation, which maximum moment we can use WL over 2 over 10, which is less value, which is going to help. But we are considering the effect of continuous or simple span. But in the example, we are using the simple span effect. So, let me check with the equation. Okay, short shear dimension lumber, shear for plywood, deflection. Let me take a screenshot from this equation, which I think this would be very helpful for us. Copy, put it here, paste, and also for the deflection, which copy, and also comes here and put it in the bottom of this one, paste. Okay, let's go review the book. Continue. This is the example. This example has two different cases, case number 1 and case number 2. What is important in the example that we should consider that the maximum concrete pressure is 900 psf. And case 1 include the plywood in a weak direction. What's the meaning of weak direction? It means that our grain is perpendicular to the span. Okay? That's it. Small studs, small Walers, and snap ties that is going to be used. Case 2, plywood in a strong direction. We can see the two cases and different of these one. For the case number 1, it is going to use 5 over 8 inches. 5 over 8 inches BB. Okay, let me review it here. It's a 5. Let me bring the example. Okay, this is very important. Copy. This is the example. Okay, let's go step by step. We want to solve this problem. Just let me. Okay, for the plywood 5 over 8 BB OES used in the weak direction. Okay, we can come over here. That's where I put the plywood information. I think I didn't put it, so I will go take from this table. Let's take this table, copy, put it here. Okay, and also this is the 5 over 8 inches on the weak axis. So IB, this is the information that we need. IB over Q. Oh, IB over Q, and the other one S for the week. IB is 3199 and S is 0.164. Okay, let me make sure I use the. Okay, for the first equation we are going to check based on the bending. We are going to use, we are going to use these this equation. L equal to, we are going to use, where is the pointer? We are going to use this equation. We are going to use this equation. Okay. L equal to 10.95 multiplied by FBS over W. Our W is 900. I think 900 PSF. Okay, if we multiply by for 1 feet, it would be 900 PLF as a linear foot. Okay, 10.95 multiply for FB. FB comes from this table. FB comes from 600. 1600 multiplied by S. S was 0.164 divided by 900, and it will gives the value in inches. Everything that we receive here is inches. L in inch. In inch. In this equation, we can see the L is based on the inch. So this value would be 5.91 inches. Okay, we have the second, this one for bending. Let me bending. Okay, this is for bending. For shear, the equation is for shear, the equation is L FV IBQ 0.6 W. So L, this is in foot. Okay, in span in FT. Okay, it would be FV. We calculate FV from this table. FV for 60 would be 60 multiplied by IB over 8 for 3.119, 6.6 and 900. The value would be, this is 1, this is 1. Okay, the value would be 60 multiplied by divided by 0.6 multiplied 900. And this is in feet. If multiplied by 12, it will be in inches. Let's see, multiplied by 12 inch, the result would be 4.1 inches. This would be the second criteria based on the shear, and the third one is based on the deflection. For the deflection, if we go up, we have this equation. Let me write it down. 1.5 1.69 to the 3 E I over W. So if we put the L, this L is also in inches, L inches. So it would be 1.69 multiplied by E. Our E comes from this table 1533000 1500 and 30 multiplied by over I for the week is, this is for week orientation, 27 over 900 to the power of 1 over 3. Okay, over 900 it would be L to the power of 3. So calculator, 1.69 multiplied by parenthesis 1500123 multiplied by 027 divided by 900 to the power of 1 divided by 3. 6 inches. Let me review my answer with inch. Now we have 3 bending, shear and deflection, and the minimum of all of these, the minimum of bending and shear and deflection is minimum is 4.1 inch, which is we use 4 inches spacing. We don't give the contractor, okay, we don't give the contractor okay, let's use 4.1 inch. Let me review here. 4.16 and the minimum is for here and the minimum is 4.2. okay, this is, and we are going to use, let's explain one more thing. This is our sheeting. Let's say this is our sheeting. Our sheeting is in a weak direction, so basically this is our sheeting grain. The red one is our sheeting grain. Just to understand, now we are knowing it's in a week. This blue one is, this is our stud. Okay, and so far, based on the sheeting that we have and our studies based on the case 1, we can see our studies based on the case 1 is 2x4. So our stud is also 2x4. 2x4, and normally we put our stud something like this to use a strong axis. Okay, so the center by center spacing, it would be 4.2 plus, and the 2x4 we have normally when a 2x4 is 1.5 inch, 3.5 inch. Okay, plus 1.5 inches. This would be the center to center, would be 5.7 inches center. 5.7 center to center. I know my voice, when you're watching the video, my voice would come earlier than what I'm writing. I hope it's something that you can bear. Again, I'm just solving for myself. It's not a teaching class. I'm not teaching. obviously there is some kind of mistake in the calculation. Okay, so far I'm in a good place. Everything is solid. What the book is doing right now is comparing the strong axis and the weak axis. Again, what is the strong axis? A strong axis is our grain is parallel to the span. Weak axis, our grain, wood grain in the sheeting is perpendicular to the span. Okay, for the case 2, use all these 3 equations and comes up with these numbers. For example, we can compare. For the bending criteria, we calculated only 5.9 inches, the maximum spacing, but it here came with 9 inches. For the shear plywood, the shear it's 4 inches, now it's 9 inches. For the deflection, we had 6 inches, now it's 11 inches. The minimum of these value is 9 inches. And for the case 2, we can see it here. For the case 2, we are using 4 by 4, which is the width of the member is bigger. Then if we want to calculate the center to center of our member, it would be 9 inches plus a 4 by 4 width, which is 3.5 inches. The maximum would be 12 or something. 12.5 on center. Okay, now we calculated our space. Basically what sheeting gives us is the spacing of the stud. Now we have the spacing of our stud. What it gives to us, if we multiply the pressure by this spacing of these studs, we have the loads on our stud. Then again we go back to the equations and calculate the maximum length that this stud can be without any Waler. Waler is going to act as a support. Without any support, to be in allowable stress range. Basically, based on these 3 equations, we calculated. We are going to calculate the maximum this length. That the equation also a little bit different, especially for the shear. The equation for the bending is similar. We can see here. The other thing that is different, now we are using Douglas fir. So we are using the Douglas fir material properties, obviously. The E is similar, but the FB, what was the FB? FB was the bending. Here you can see the FB for the bending material properties is only 1000. So we go back to let's solve the example for this part. I did not solve the case 2 for the sheeting because case 2 for the sheeting is similar. Just let me put a note case 2 in the book. Okay, case 2 in the book, we can review. Now we go on the stud design. What was the equation for the stud? Equation for bending is similar, 1.95. It's exactly like this. Let me go back here. The equation for the stud, it looks like here. Let me write the equation here. It looks like I have 2 different pages. It's very hard to manage, to be honest, but let's see. For bending equation would be similar, 1.95 square root of FBS to the W. Our W is 900 multiplied by the maximum spacing is right now 4.2. Let's see, 4 inches divided by 12. let's the center, let's get it center to center. So it's 5.7 inches. 5.7 inches divided by 12, our W for a stud. Let me, oh my god, our W for a stud would be this value. 900 multiplied by 0.47 divided by 12, it's of PLF. So in this equation we have 1.95 multiplied by square root of 1000 for what is the S? S is for the stud is here 2 by 4 and the S is 2 4 to the power of 2 over 6. It's 32 divided by 6, it's 5.3. BD2 over 6. So let me just double check. Okay, it's not we should use 1.5 to the 3.5 to the 2 over 6. 1.5 multiplied 3.5 to the 2 divided by 6. 30625. 30. The mistake that I did is I put 2 and 4 in the equation, but since it's 2 by 4, it's 1.5 multiplied by 3.5. Okay, this is inch to the 3062. I have to look over there, and divided by 427.5, and this value is in inches. Okay, let me calculate 1.95 multiplied by radical 1000 multiplied by 3.062 divided by 5.21 inches. This is now this is the length of the stud member. If this is the stud, it means let's say we have only the bending criteria. Based on the bending, if and we are going to decide based on the bending. So this means that our stud should support it somehow, in this case by Waler, and the maximum span it should be 5.2 inches. Okay, is it I'm talking to myself. Okay, it's 10.95. I made a mistake. 10.95. So multiply by 1000. The equation is similar. 10.95 multiply by, why my value is different? 1000 3. 29.3, and this would be 29 inches. 29 inches, 0.3. Okay, Now this is the bending. We are going to do the same for the shear. What was the shear equation? The difference here is the shear equation, as we had here for the shear equation is different. This is for plywood, this is for dimensional number. We use this equation for the shear, F prime V B D 0.9 W plus 2D over 12. As you can see here, it used this equation. For this equation, F prime V. F prime V we can use if we come back in here and go to the table. F prime V is 2 times of 95. Why do we use 2 times? Because the ACI let us we use 2 times of 95. So 2 multiplied by 95, it would be 190. As you can see here, 190 multiplied by B. The B is your stud width, which is 1.5 inch. D is your stud height, which is 3.5 inch, divided by 0.9 W. What is your W for 27.5? Plus 2D over 12. This value gives us 38 inches. And the other criteria, I couldn't find a better word right now. So far, I'm telling the deflection limit. Let's call it limit. The deflection limit is 44 inches. We have 3 different values so far for the stud maximum free span length. 44.9, 38, and also 29 from the bending, which obviously bending is here. So we can use 29 as our free. Plus, what is it doing? Okay, this is for case 2, and also solve the problem for the case 2, and calculated this value. For the case 1, the maximum was, the minimum of all 3 is 20.9 inch. The spacing of the Walers. Now we calculated the maximum, which is 20.93. Okay, what this value gives us, this is the value if multiplied by this value by 900, I guess. Now we are so far we calculated the spacing for the studs and the spacing for the Waler. So we have the Waler. Imagine that this is the continuous member, and we have a Waler here. The loads on the Waler is 900 let's go on the part 3. Let me zoom out. Part 3 Waler. The load, the W is 900 multiplied by 29.3 divided by 12. It would be 900 multiplied by 29.3 divided by 12 is 2197.5, which is pound per linear foot on a Waler. The difference between the Waler and the studs is the Waler. Now we have a beam. The Waler is double. The Walers are the double section. So everything that we have in the, let me write it, make it in blue. So every section properties that we had is going to be double. Our I, our S, our A, everything is going to be doubled. Okay, so we have a beam like this, we have a load on acting on this one, and again we have 3 different criteria. Based on three different criteria, we are going to calculate the spacing of the tie. These ties are going to hold these Walers. Okay, the spacing of the tie spacing. Let's go back on the book. It's already 1 hour video. I'm gonna finish it after this section. This is the properties of a double Waler, which is section modulus is 2 times, and base dimension is also 2 times, moment of inertia is also 2 times. For the bending criteria, again, bending FB is 1000 psi, shear is 2 times of 95 psi, and E is 1,500,000 psi. The W is 29.31900 divided by 12. Mine is a little bit different, but it's almost close. I don't know what mistake I did, but this value is 2197, but in here is 2205. It's okay. We will continue with this value. For the bending, we calculated 80.2 inches. This gives us the spacing between the ties. This tie to its minimum should be 18 inches. For the shear, it gives us, okay, it can be 19 inches. For the deflection, it will say, okay, it can be a space 32.8 inches. Which one of these L we use? We use the minimum one, which is 18.2 inches. And this one is for the case 1. Similarly, we have every this step for case 2. And let me read this part. This is important. So, okay, 80.2 inches. Now we want to calculate the ties. The tie loading is the pressure comes from this. Let's say we have a loading, we have a capacity. So just a second. Sorry. So far now we are at step 4 to calculate the tie capacity. The tie capacity is just calculate. Imagine that we have an area with a pressure, and we want to calculate the amount of load at a specific point. So we multiply the area by the pressure that we have, which in our case 900 multiplied by the distance between the stud and the distance between the Walers. So 900 multiplied by 18 inches divided by 12 to turn it into the feet, and 29 inches divided by 12. So it gives us the 3,333 pound in tension. It means each of these, let me explain it here again. Open, please. Let me. This is our first formwork. This is our second formwork, and this is our ties. And each of these ties, let's say this is our stud layout, and this is our Waler layout, and to be honest, it should be something like this. This value comes 3,003 pound in tension. Now we go use a tie that has this capacity. For example, a 3,500 pound tie would be okay for in this case, which normally we want to have some kind of safety factor, so we use a stronger tie. And for case 2, we use a 12,000 pound tie. And here is the end of the example. Let me review the what remained from this chapter. Example, formwork chart. There is another example which I'm gonna review it in the next video, but let's review this table. For the case 1, we use case 2. Remember, what was the case 1? Case 1, the most important one is that our shear was acting in a weak direction, which our grain is perpendicular to the span. The second, we had a stud 2x4. What is the second case? The shear acting in a strong axis, which is the grain of the wood is parallel to the span of the stud. And also a stud is 4x4. Based on that, our Waler is 2 times 4x4 in case 2, and our Waler in case 1 is 2 times 2x4. And also the snap tie in case 1 that we need is only 3000, which for case 2 we need some she bolt or something, which I'm not familiar in Canadian, which I need to review it more for these type of bolts, but it's 9000 that we need. So for the spacing between studs in a case 1 is 5.7, which is 12.5, which is, it means we can use longer span since we are using the sheeting in a strong axis, our plywood in a strong axis. Waler spacing is also similar. You know why the Waler spacing is also similar? Because in this case the stud spacing is longer, is almost 2 times, and it will make it the area of load on a Waler is bigger. That's why the Waler spacing is close and similar. And the tie spacing, which is very maximum 18 inches, but in with this weaker lower capacity ties, but in here we can use 4 times spacing with obviously stronger ties. Okay, thank you. I'm sure and I know that I had a lot of grammar and pronunciation and also technical mistake while I was talking, but my main objective by recording this is that you guys know, okay, if you want to, for any reason in any future company, if you want to design a formwork, you can use this book and you can review. Also, you have a video that might be helpful for you. Thank you for watching the video. Bye for now.